first we're going to start off with atomic structure. So firstly, starting at the very beginning with chemistry, the periodic table. All elements on the periodic table have two values on them, the atomic number and the atomic weight. So the atomic number is right up here under the name of the element, carbon, which is 6. And the atomic weight is the one here at the bottom, the 12.011. As you remember, atoms always have an equal number of protons and electrons in their standard form. And it's in quotations because this is what we call the atomic form. But you can think of the atomic form as this is like the standard form. This is the generic form that it will normally be found in. And anything other than that, like maybe an ion form, is something out of the ordinary. It's something special. Okay, and this this atomic number is it's unique to each element. So, for example, for carbon, it's always 6, and it's while the electrons may be different for sometimes from this atomic number. For example, you can have carbon with 5 or 7 or more electrons, but you can never have carbon with more or less protons than 6, right? If it somehow gains a proton from something else, it gets 7 protons, and now it's no longer carbon, now it's nitrogen, right? And this is the whole principle behind like nuclear chemistry, nuclear fusion, nuclear fission. You can turn one element into another element, but so know that if you have carbon, always, without exception, it has 6 protons, right? And that's the atomic number. In addition to protons and electrons, atoms also have neutrons, which have mass but no charge. Remember, electrons have charge but no mass. At least in chemistry, in physics, they do have a mass sometimes, but in chemistry, we consider that they don't have mass because it's so small. The sum of the mass of the protons and neutrons is called the atomic weight, that 12.011 number for carbon. And a very important note, the weight shown on the periodic table for each element is the weighted average of all the masses that element can be in. So unlike with electrons and protons that have a very fixed number of protons and electrons, an atom can have a varying number of neutrons, right? So for example, even though on the periodic table, carbon has a weight of 12.01, which would make you think there's 6.01 neutrons, which by itself doesn't even make sense, right? How can you have 0.01 of a neutron? Well, it's because there's actually a 12 weight variant of carbon, a 13 weight variant of carbon, and a 14 weight variant of carbon, which this is the proper nomenclature for that. Okay, C12, C13, and C14. The weight shown on the periodic table is the weighted average based on abundance. So since 99% of all the carbon is in the C12 form, the weighted average is very close to 12. But because the 13 and 14 variants do exist, it's slightly higher than 12 because it averages, because of the average, okay? And these variants, the C12, C13, C14, are called isotopes of each other. An isotope is essentially just the same atom, carbon, but with different amounts of neutrons and different atomic weights as a result. So C12, C13, C14. And in the case of carbon, it's very lopsided towards one weight. So it's pretty much almost exclusively in the 12 range. But for other atoms, like for example, chlorine, it's a lot more mixed. So I believe it's chlorine 34 and 36 are the two most abundant ones. So I think on the periodic table, it has a weight of about 35. But essentially, you don't really see chlorine 35. You see a pretty evener mix of 34 and 36, which averages out to 35. Okay. Next, I'm sure you've seen this diagram hundreds of times, is the electron atomic model, which shows the electron shells as well as the nucleus in the middle filled with protons and neutrons, right? So remember that both protons and neutrons are found in the center, like in a packed nucleus, right? Similar to the nucleus of a cell, but a little bit different. Meanwhile, electrons are found in multiple layers or shells or like rings orbiting this central nucleus, right? Then there's different layers. So for example, this first layer, then this bigger second layer, and so on and so forth. These shells have a set number of electrons they can hold, and obviously the further away from the nucleus they are, the more electrons they can hold. because the rings are bigger. So for example, this ring is kind of small, this one is bigger. Then if you add more rings, this one's a little bit bigger, this one's even bigger, and they can, obviously, the bigger the shells are, the more electrons each shell can hold. Okay. And then these are orbital configurations. Again, I'm sure you've seen many times. This is how we organize the electrons into these shells or into these orbitals, right? I have the list here of how usually the orbitals go, or the electrons get put into orbitals, the order in which they get put in. This is based on energy, which configuration is the most energetically stable and favorable and whatever. We're not going to get too deep into that because it's not as important, but just know that usually this is the case. Each atom fills the orbital shells differently due to them having different numbers of electrons, obviously. This is the general pattern, but if you really wanted, there are many exceptions. This is one part of chemistry that has a ton of exceptions. So if you really wanted to know all the exceptions, you would have to kind of learn each one independently. I wouldn't strongly encourage it because it's not that important. It's not that serious, at least for the MCAT. But if you want to be safe, then that's really the best way to know it for sure. But there are some general rules apart from this order. So usually, as you can see here, so there's the S shell, and then followed by the P shell, and then the D shell, and so on. So the S shell can hold 2 electrons, the P shell can hold 6 because it has 3 boxes, and then the D shell can hold 5 actually, like this. Then it can hold one 10 because each box holds 2, right? And each level hold, you get just drawn 2 extra boxes as 1 box. Then the P shell has 3 boxes, and this is 5 boxes, right? So the general rule is usually atoms prefer to have 1 electron per box rather than start filling up the boxes any differently. So for example, we can take carbon over here. So I'm going to draw it again. So it has 2 electrons that go into this P shell because these are filled, but it only has 2 to fill this P shell, which normally has 6. So the 2 options really are 2 in the first box, and then the rest of the box is blank. Or what you see here, where each box, or the first 2 boxes have 1 each, and then the third one is blank. Usually it will prefer to do this before it does this. And you can see that again here for nitrogen. Instead of filling up 1 fully, it actually prefers to fill them all up by 1. Same thing again here with oxygen, fills up all of them, then it goes for another one, instead of maybe doubling up on 1 and keeping this one empty. Doesn't really like to do that, okay? So that's a general rule. Another general rule is that d orbitals are usually filled after the s of the following level, but that's not actually in all cases. So you can see here, this first number is which shell we're talking about, which ring. So the 1 here means this is the first ring. These are from the second ring. These are the third ring. But you see here goes 3s, 3p, 4s, then 3d, right? So this is again because the 3d is actually higher energy than the 4s. So the 4s actually gets filled up first before the 3d. Usually in many cases, but not in other cases. It varies again. This is something that you would have to kind of look at a case by case, but usually, and it's kind of safe if you really don't know, and it comes up on the test day, which is kind of rare, but if it does, know that I think it's a safer bet to say that 4s gets filled up before 3d. Okay, so that's again just a general thing. But many of these you'll just have to memorize, or you'll have to understand them. Luckily, this is very low yield, and you very rarely will see these orbitals. They'll ask you to fill up these orbitals or say something about these orbitals. But in case they do, this is something, and it's even rare that they'll give you a curveball. So, okay. Next up is Lewis dot structures. So for all atoms, the last filled shell is called the valence shell. So for example, we have here we have this ring, which is the 1s ring, right? And you can see actually it only has 2 electrons because it's the 1s ring, which only has 2. Then this is the 2s, and then the 2p ring, I guess, as well. This says 2s, 2, and then has these 3 are for the p, going to the p orbital, right? And because this is the most outer ring, or the last ring, this is called the valence shell, right? And these 5 electrons would be the valence electrons, right? These are special compared to the other electrons because these are actually the electrons that are used for bonding usually. Many of you have likely learned Lewis dot structures, which specifically is a way to draw atoms to help visualize specifically the valence shell and the valence electrons, right? So if we want to look at nitrogen, which is right here, you can see its valence shell is 2 because there's 2s2 and 2p3, has actually 5. So it has 2 in the s shell and 3 in the p shell, right? Which is a total of 5 valence electrons. So you just write the element and then you do 1 nitrogen on this side, 1 atom on this, 1 electron on this side, 1 on this side, 1 on this side. So that's 4. Now you need to have a 5th one, so you can just put it anywhere because it doesn't really matter, right? Now this one is paired up. This is a pair. This has 1, so it's missing a pair. This has 1, so it's missing a pair. And this has 1, so it's missing a pair. Most of them will usually only have 4. Not always. Some have 6. Some can have 5 or 6 actually. Mainly like sulfur. Think sulfur, fluorine can have, and we'll actually cover that a little bit later. But yeah, but most have these 4, right? They can have a pair, or they can only have 1 for the atom at least. Now let's do something a little more complicated. Let's do the Lewis dot structure for H2O water, right? So we know that H has a valence electron, only has 1 valence electron. So these only have 1 dot. Oxygen has 6, so it has 1 dot here, 1 here, 1 here, 1 here. Then we double up here and here. So now this is missing its pair, this is paired, this is paired, this is missing 1, this is missing 1, and this is missing 1. Well, these don't really like to be missing 1, so they want to fill their pair. So how would these 2 hydrogens fill their pair, and how would this oxygen fill its 2 pairs? Well, actually, what they can do is they can just join and join together like this, right? So this has 1 and this has 1. So what are you doing? You each have 1, and then you want to make 2. Just share them. And what you're left with is this. So these are 2 it came with. This is hydrogen's 1. This is oxygen's 1. And this is this hydrogen's 1 and oxygen's other 1, right? And now look, they're shared. And now everybody's perfectly paired up and everybody's happy. And this is the basic principle behind a bond. This is what a bond is, just essentially a sharing of electrons. And the way we draw that is actually like this. And then we can draw the 2 lone pairs. And that'll be the Lewis dot structure for H2O. And you can do similar steps for basically any compound, right? Any compound would have the same thing. Bonds, each bond represents, each line for a bond represents 2 electrons, right? A bonded pair. Okay. Now, let's find the geometric structure. Now that we know how to do Lewis structures very easily for compounds, it should be pretty easy to guess the geometric structure of most compounds. First, you have to see how many electron pairs the structure has. For example, H2O, as we just talked about, has 4. So it has, let's see, oxygen. Again, we'll just draw this like this, and dot, 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 right? So it has 4. Remember, this is 2, this is 1, this is 1, this is 1, and this is 1, so that's 4. Out of these, you have to see how many of these are lone pairs. Lone pairs are just these dots that are not bonded. So it has 2 lone pairs and then 2 bonded pairs. So I'll try BP and LP. Okay. And you just have to, I'll show you the table in the next slide, but usually you won't have a table, you'll actually have to memorize it, but for now, I'll show you the table and the diagram on the next slide. But you just match up the number of bonded pairs to the appropriate structure in your head. And so 4 pairs, going back to this, 4 pairs is a tetrahedral shape, which I'll draw here as the oxygen. Tetrahedral just means like this, essentially. Right, and this dotted line means it's going behind the screen, so it's like 3D, right? And tetrahedral, all of the lines are equally spaced from each other. So one is going up, one is going to each side, and then one's going up, one's going up, one's going to this side, one's going to this side. You can see here, one's going behind towards me. Okay. And they're all equidistant from each other. So the angle between this one and this one is the same. Between this one and this one is the same. This one and this one in the back is the same. And then this one and this one in the back is the same. Okay. And this one, the top one, and the one in the back is also the same. Right. It's all the same angle. Right. They're all equidistant. That's what tetrahedral means. But now we have to remember that we have this tetrahedral. I'll draw again here. But on this tetrahedral, this is a hydrogen, and this is a hydrogen. This is a lone pair, and this is a lone pair. We actually don't draw the lone pair, so we actually can cross this out. And this is also a lone pair, so we can just cross this out. And now all we're left with is this. Right? You don't change anything. You keep it the exact same shape it was before. So you see how it had these lines? It was like kind of like bent. So you just keep it like that. And we can just redraw getting rid of the lines for the lone pairs. And this is the geometric shape of water, right? Notice how it's bent. A lot of people draw water like this. This is wrong. This is linear. There are molecules that are linear. For example, CO2 is linear. But water is not linear. Water is bent. Specifically, that's the name of the configuration, bent. Okay, and just to explain everything I've just been going over, just to show you, we have, like I said, linear. When you have 2, so this number on the left, this is how many total pairs it has, right? So for example, water had 4 pairs at the start, the 2 lone pairs and the 2 bonded pairs. That's 4 pairs. So we started off with this. When you start off with this, you start off with a tetrahedral. Once you start off with, and this is what it looks like. Remember, the dashed line goes towards you, and this one's going back, right? They're all equidistant. Now, once you start off with 4, how many lone pairs does that have? Well, if it has 1 lone pair, let's do this one at the top. Doesn't matter, but let's do this one at the top. You can just cancel that out. Now you're left with just this. Well, what if there's 2 lone pairs? Now you have to cancel this one out. You have to cancel this other one out. And you're left with essentially just this, which is the bent configuration, and it's water. Right? If you have 4, but you only had 1 lone pair, so for example, they gave here NH3, you actually have a trigonal planar, trigonal pyramidal, right? So it looks like a pyramid. If you just connect these lines, it's a triangle base for a pyramid, and then it's coming up, right? So it makes triangular pyramid, right? If you have no lone pairs, you don't cancel anything out, you just have tetrahedral. If you start off with only 2, it's called linear. If you start off with 3, it's planar, and then you get rid of 1 and you get bent. So there's actually 2 ways to get bent. You can get bent this way, starting off with tetrahedral and eliminating 2, or starting off with a trigonal planar and getting rid of 1. Then if you have 5, which I mentioned, there's some elements that do, like here we have phosphorus, sulfur, bromine, chlorine. These can have 4. These have 5, 6 pairs. 5, 6 pairs, yeah. So if you have 5, you start off with a pyramid, right? This is just the same triangular base pyramid going up as it was before. But now you also have a pyramid going down, so it's a bipyramid. So it's a pyramid both ways with a triangular base. You get rid of one, and you're just left with the seesaw. Get rid of another, you're left with the T, right? Get rid of another, you're left with linear. Again, two ways to make linear. Octahedral, it's a square bipyramid, so it's a square base. Goes up, 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 and then down, 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 and then down. Essentially, square base and a pyramid up and a pyramid down. Get rid of one, you're just left with essentially just a pyramid in one way, in one direction, which is up. There you go. And notice you just got rid of this and all the connecting lines. And then square planar, you get rid of this as well, and then you're just left with a square. Right? Very simple. This you have to memorize. There's not really any way around it. You just have to memorize it, but it's not that complicated. I think at least just to memorize this, not compared to some of the other stuff that you have to memorize for biochemistry especially. So I think this shouldn't be too bad, hopefully. And looking at a diagram really does help. Another thing that you should memorize for each geometry is also the bond angles that it makes. So for example, obviously for linear, it's not that complicated. If you have just a straight line, the angles between them is just 180 degrees because it's a straight line. If you have just a triangular plane, 120, 120, 120, it makes 360. If you have a bent, it's 118. This one's really important, tetrahedral. And tetrahedrals are actually very common molecular geometry because a lot of carbon bonds, especially for organic chemistry, biochemistry, a lot of carbon bonds are tetrahedral. So tetrahedral, especially in the body, is found a lot in organic chemistry and biochemistry. So yeah, and the angle is 109.5 degrees between these, this, right? The angle between each of them is 109.5. For the trigonal bipyramid, it's between the bottom and the top and any of the sides. So these guys, it's 90 degrees, and same thing for the bottom, it's 90 degrees, right? Because you can see here there's right angles. Right angle right here, right angle right here. Okay, and you have to think of it a little bit in 3D, so it's hard to see, but yeah. But it's also at its core a triangular base, so the angle between this and this is just like in the planar is 120, right here and right here. Okay. Octahedral, 90 degree in all directions, 90 degree like this from the bottom and the sides, and also the sides it's a square, so it's just 90s between them. Okay, very simple. And square pyramid is obviously the same thing, square planar, T-shape, linear, those are very easy to figure out. Okay. So I recommend memorizing some of these as well. Okay. Yeah, now let's do a clicker question. What are the bond angles in iron 3 acetyl acetonate? And this is a very, I would say, realistic question that you might see accompanying a passage. Obviously, you don't know what iron 3 acetyl acetonate looks like. I don't either. But since it's accompanying a passage, in the passage, usually in a figure, they'll actually show you what it looks like, and I've included it here. So this is something that they might show you. It's just an iron, which they know is iron 3, right? And 6 oxygen things, right? And they're just going to ask you to find what the angle between them is. Okay. So what? Again, what are the bonds? Sorry, I have to fix my recording. Okay. Give you guys 30 seconds, and so the correct answer is only 90, and let's talk about why that is. So as you can see here, iron has 1, 2, 3, 4, 5, 6 bonds to this oxygen. Therefore, we can just draw it in 3D structure. You can skip the Lewis dot structure because we don't really need to, because it's already shown here that it has 6 bonds. So essentially, it's kind of like a Lewis dot structure. And remember, 6 bonds looks like this. And I'll just write each of these as an O. Right, and then if you connect these, this is a square pyramid. Sorry, it looks kind of bad, but just pretend. It's a square bipyramid. I think it's called an octahedral. And there are no lone pairs because it has 6 bonds. So really easily, you can just see either through your own memorization of what an octahedral has, which is only 90-degree angles, or you can actually just see it 90-degree, 90-degree. All of these are 90 degrees. Right here, right here, right here. All of these are 90 degrees between every bond angle, okay? Okay, and that just gives you 90 degrees, right? So really that question was actually very simple if you just really knew what to do, which was, okay, this, I have to know the geometry. What is the geometry? Okay, well, it's not octahedral because it has 6 bonds, right? You go back to this. If it has 6 bonds, so static number 6, it must be an octahedral. Okay, how many lone pairs does it have? Okay, no, it has no lone pairs because they're all bonded. So it must be an octahedral, must stay an octahedral. So octahedral now has all 90-degree angles. And that's it. That's the answer. Okay.